Today we're going to be having our final lecture on smooth analysis. So this idea of problem instances which are sort of chosen worst case by an adversary but then subjected to a small perturbation by nature. And smooth analysis, historically, and also the last couple lectures, the emphasis has been on you study some fixed algorithm of interest. For example, the simplex algorithm or local search or whatever. And you want to understand that algorithm through the lens of smooth analysis. Whereas in this lecture, rather than trying to understand algorithms, we're going to try to understand computational problems through the lens of smooth analysis. So we're going to see what we can learn about essentially computational complexity by seeking out algorithms with polynomial smooth complexity. The answer will actually be very crisp, at least within a certain natural class of problems. The answer will essentially be if and only if, that is, the smooth complexity is polynomial if and only if the worst case complexity is pseudopolynomial. And I'll remind you what that means in a second. Okay, but to make this a crisp if and only if statement, we should zoom in on some class of problems so we know what we're talking about. So let me start with that. So we're going to talk about binary optimization problems of a particular form. And there's many, many canonical examples. For now, think of knapsack as being a canonical example. One of the things that we've talked about before that we want to generalize. So there's going to be n variables and they're binary. So x1 up to xn. These are either 0 or 1. For example, xi could denote whether or not you're including item I in some knapsack. And then some of the 0, 1 vectors are feasible. And we're going to handle that in a very abstract way. So we just have some feasible set F, which is some arbitrary subset of all possible 0, 1 n vectors. For example, in the knapsack problem, F would denote the characteristic vectors of all of the subsets of items who fit in the knapsack. Okay, that'd be one example. There are values, again, just like in the knapsack problem. And the goal then, abstractly, is just to compute the feasible solution with the maximum possible value. Okay. So compute x and f, and again, remember here, x is a n-bit vector, maximizing v transpose x, also known as sum over the n coordinates of vi times xi. Again, remember, xi is always going to be 0 or 1 in this lecture. Okay? So I'd like to make that as big as possible, subject to the feasibility constraints. Actually, minimization would be fine too for everything we're going to say in this lecture. I'll stick with maximization for consistency, but you can even think of the v's as being negative if you like, and then it's basically a minimization problem. Okay. So like I said, one example I want you to keep in mind for concreteness is knapsack. But let's point out that you can encode many, many problems with this formalism. And in fact, the worst case complexity of the problem will vary depending on how you choose capital F, the feasible region. There'll be some choices of capital F that lead to a much easier problem than knapsack. So for example, I could define capital F to just be at most k of the coordinates of x. Say at most 10 of the coordinates of x are 1. That would be very easy to solve. You just sort by the VIs and pick the top 10 VIs, and that would give you an optimal solution. Or you can encode problems far harder than knapsack in this formalism. For example, capital F could denote the characteristic vectors of independent sets in some graph. Okay? So as you vary F, you get different problems. All right? But so there are these n things, you choose them or not, but then there are also these global constraints encoded by capital F on which combinations are allowed and which are not. Okay. Any questions on that?
Arthur, is there a general approach to solving binary optimization problems?
Well, so it depends if you mean in polynomial time or not. If you don't mean in polynomial time, then integer programming would be one obvious approach. If you mean in polynomial time, well then, you get this plethora of different NP-complete problems, and as we know, different heuristics seem appropriate for different problems, so you would not expect some useful meta-algorithm covering all of them. Okay. So, and in this lecture in particular, we're not going to say some sweeping positive result for all of these, but what we'll be able to say is among problems of this form, one good thing is true if and only if a different good thing is true. Okay, smooth polynomial complexity if and only if pseudo-polynomial time worst case complexity. Okay, so that statement will make within sort of the realm of these binary optimization problems. Okay, and of course there'll be plenty of problems for which both of those are false, like independent set, for example. Okay. Let me give you another. I do want to point out that there will be implications for the main result of this lecture, not just for knapsack, so we'll also get results that we don't know. So let me just sort of sketch a quick second application now, and I'll ask you to think about it a little bit more on homework number 8. So let me talk about a scheduling problem. So suppose you're given n jobs, which each has 3 parameters. So depending on which homework problems you've done, you may have seen things like this. So let's say each job has a processing time pj, that's how long it takes to execute. We're thinking about just having a single machine. Okay, so you're just trying to figure out how to sequence n jobs on a single machine. Each machine has some amount of time that it takes to run, assume you even know what that is. Each job has a deadline. Okay, so you're welcome to think of these as, you know, the homework assignments that you have at any given time. You have an estimate of how long it's going to take. You know when it's due. Now, unfortunately, you're so overscheduled, you're actually not going to be able to complete all of the jobs by all of the deadlines. So you're going to have to make some hard decisions. And there's a cost, CJ, which is the penalty you incur if you fail to complete job J by the time of deadline DJ. Okay? And then the objective here is to minimize the total cost that you incur for all of the jobs that you fail to meet by their respective deadlines. Okay? So you want to minimize the cost of the late jobs. All right. So that's I hope you all agree that's a well-defined computational problem. It may not be obvious how to solve it, but I hope it's clear what it is, what it's asking you to do. Okay. So on homework 8, I'll ask you to give a pseudo-polynomial time algorithm for this problem. Okay, so a dynamic programming-based algorithm, you know, very much sort of in the spirit of what you know from knapsack problems. Okay, and the reason I'm going to ask you to do that is because we're going to, in this lecture, have a positive result for all problems that have pseudo-polynomial time algorithms. Okay, we already know knapsack does. This is just meant to show you a second application of sort of the meta theorem, the general theorem we're going to have today. Okay. So that's all I was planning on saying about this. But here's, you know, just again, proof of concepts. There's multiple things we're talking about at once. Probably the simplest thing for you to do is just keep knapsack as the canonical example in your mind as we go through the lecture. Okay. All right, so homework, pseudo-polynomial time. Okay, so it is NP hard, but it can be solved in pseudo-polynomial time. All right. So, back to the question about this lecture. Which problems admit smooth polynomial time algorithms, specifically which binary optimization problems admit them? So as usual, we have to be precise about what we mean by smooth complexity. And it's going to mean the same thing as in the last 2 lectures. So we're going to have this very pleasingly kind of agnostic or general notion of smooth instances. So each VI, okay, so these are pretty much the only numbers, right, in this abstract binary optimization problem. So if something's going to be perturbed, at least the way I've written it so far, it seems like it's got to be the VIs, right? So each VI is drawn independently from a density function f sub I from 0, 1 to 0, 1 over sigma, okay? So this is exactly what we were doing last lecture when we talked about Pareto curves of knapsacks. Is basically what we were doing when we were talking about TSP in the plane as well. So notice that I'm scaling the values in effect to lie between 0 and 1. It's more or less without loss of generality. And then again, the assumption is that the distributions are not too spiky. Okay, the density is everywhere bounded above by 1 over sigma. So the area of support in particular has to be at least sigma. Okay, so it's at least a little bit spread out everywhere. Okay, so and then as usual, what are we going to mean by having polynomial smooth complexity? We mean there exists an algorithm with smooth polynomial time, running time, meaning its running time is polynomial in the input size n and in 1 over sigma. Okay, so we mean the same thing as in the last couple of lectures. So that's what we're asking. Which binary optimization problems admit an algorithm whose expected running time, where the expectation is over the perturbation, whose expected running time is polynomial in n and 1 over sigma? That's the formal question. All right. And so, as I said, there's a very satisfying answer to that question on the left, if and only if solvable in randomized pseudopolynomial time. Okay? That's what it means. All right, so let me remind you a little bit about what it means to be pseudopolynomial time. So normally when we talk about that, we're thinking as the numbers as being integers, although really whenever you have anything in finite precision, by scaling, you can think of them as integers as you want. It's just some binary encoding. So pseudopolynomial time means you can run in time proportional or polynomial in the magnitude of the values of the numbers in the input. Okay, so for example, in knapsack, you can run in time maybe polynomial in the knapsack capacity, capital W. This is not a polynomial time algorithm, because polynomial time always means polynomial in the amount of bits it takes to represent the input, the number of keystrokes required to actually describe the problem. Right, so if your knapsack capacity is 1 billion, it does not take 1 billion keystrokes to describe that capacity. Okay, it takes about 10 on your keyboard. So log of the magnitude of the number is the appropriate encoding size for numbers. Okay? So a knapsack dynamic programming algorithm, which runs in time something like n the number of items times capital W the knapsack capacity, is not polynomial, because it's not n times log W, but it's pseudopolynomial, n times W. Okay? And that's still good in many cases, right? If these numbers aren't too big and you're polynomial in them, then you're quite happy. All right? So that's one reason why you're happy with pseudopolynomial time algorithms. Okay? So this is what it means. You run in time, you can think of it either as you run in time polynomial in the magnitude of the numbers, or you get to run in time exponential in the encoding length of the numbers. Okay? Both of those are perfectly reasonable ways to think about it. All right? Okay. So, and again, this distinction is only relevant when you're talking about problems where there are numbers, right? So if we're talking about independent set in unweighted graphs, there's no numbers, right? So there's no notion of pseudopolynomial time. But when you're talking about something like a binary optimization problem where you have these V's, and the V's, depending on how you want to think about it, either the V's could be super big, or alternatively, if the V's are described to very fine precision, it's more or less the same thing by scaling, then all of a sudden this is a relevant notion. Okay? All right, but again, just think about knapsack as a concrete case of the type of problem that we're thinking about. Okay, so to go back to the theme that I mentioned at the very beginning, we're using smooth analysis in this lecture to understand algorithms, not to understand problems. So when we talked about, say, the simplex method, we said, oh, well, worst case is exponential. When we switch to a smooth model, the running time drops from exponential to polynomial. Okay, that's what we learned from smooth analysis about simplex. Here, we're learning something very interesting, which is that problems which are hard in a worst case sense suddenly become easy in a smooth sense. Okay? We go from a situation worst case where, unless p equals np, there does not exist a polynomial time algorithm, to a situation after adding these really small perturbations, there simply is a polynomial time algorithm. Well, again, expected running time over the perturbations. Okay, so the problem goes from hard to easy. Before the algorithms went from fast to slow, or sorry, from slow to fast. Now the problems go from hard to easy. And again, I mentioned this last time, but it feels surprising if you're sort of, just used to the thinking of NP completeness as a death sentence. But I mean, for the people who solve NP complete problems in practice, it's long been known that knapsack and other things that admit pseudopolynomial time algorithms do seem empirically to be amongst the easiest of the NP complete problems. So this is sort of a satisfying way that we see that actually playing out in the theorems as well. Okay. All right, there's also a connection, and this I'll ask you to think about on the homework. There's sort of a third, right? So on the left-hand side here is polysmooth complexity. Over here is pseudopolynomial time. There's a third notion, which is also roughly equivalent to the other two, which is admitting fully polynomial time approximation schemes. And that's sort of a best possible approximation result. So what that is it means, while you can't, this is now all worst case notions. Let me just write down the acronym real quick. So fully polynomial time approximation scheme. So what this algorithm does is it takes as input an instance and an approximation parameter epsilon, and it returns an approximate solution whose objective function value is within 1 plus minus epsilon of the best possible. And it does so in time polynomial in the input and polynomial in 1 over epsilon. Okay? So the point is you can't get 100% of optimal, but you can get as close as you want. Your algorithm is going to run longer and longer and longer as you want to get closer and closer and closer. But actually, most NP-complete problems are much more resilient than this. For most NP-complete problems, you cannot actually approximate them arbitrarily closely in bigger and bigger polynomial time amounts. Okay, so this is sort of the best case scenario. So that's yet another sense in which these are sort of the easiest of the NP-complete problems. So you get this sort of collapsing of all of these different notions of relatively easy NP-hard problems. Rishi?
Problems which fall into this FPTS category the same as the problems that are solvable in pseudopolynomial time?
Roughly, yeah. So that's exactly what I'll ask you to explore in the homework. Yeah, and that's somehow more folklore. That's less of a, what we'll do today, the connection between smooth complexity and pseudopolynomial has more the feel of a theorem, whereas the connection between pseudopolynomial and FPTS is a little bit more of an observation, folklore observation. So it's a good thing to think about on the homework for that reason. Yeah. Yeah, so all three of these things are more or less the same, modulo some fine print. Good. Other questions? Okay. So let's get going with the proof then. So I'm going to start by proving the slightly easier direction, which we're going to show that if you have polynomial smooth complexity, then you're solvable in randomized pseudopolynomial time. Okay? Any of these binary optimization problems. All right? So consider a binary optimization problem so that there is a smooth polynomial time algorithm, call it A. Now, what we want is we want to use A, and we want to use A really as a black box, right? We're not told anything about this thing. We're just told that it exists. So pretty much the only way we can think about using this hypothesis is kind of, running it, basically. That's the obvious thing to do. So given this, we want to somehow construct now a worst case algorithm, but that's allowed to run in pseudopolynomial time. Okay? So our goal is harder in the sense that we want a worst case guarantee, but easier in the sense that we're allowed to run slower. Pseudopolynomial instead of polynomial. Okay, so consider a worst case instance of whatever binary optimization problem we're talking about. With weights with some VIs, okay? And think of them, again, scaling if necessary. Think of these values as being integers, okay? And that's really without loss of generality when you're talking about pseudopolynomial time algorithms. All right. But so now actually, I just did this as an intermediate step. I'm going to scale the values again, because for these smooth, to have the perturbations measured correctly, we're thinking about the values as being between 0 and 1. So take this worst case instance with integer VIs, scale by the largest of the values, Vmax. Okay, there are these n values. Right now they're all integers. Divide them all by the largest. So scale by Vmax. So VIs are in 0, 1. And now here's the point of all this. So it turns out a major theme in this lecture is to understand how much better the best solution is than the second best solution. That's going to be really important today. Okay? It hasn't really, in some sense, it's like a numerical version of some of the stability clustering stability properties that we had. Those were much more complicated because they were combinatorial. Now we're just looking at the objective function value. So the gap between the best and the second best is going to be important. So think about the value of the best solution minus the value of the second best solution. And you think about this different ways. One way to think about it is suppose there was a unique solution. If there's multiple unique solution, a unique optimal solution. If there's multiple optimal solutions, put them all here. Okay? So look at the one hand of the highest objective function value that anything can get. And then amongst everything which is not optimal, look at how high you can get. Okay? So once you go to that first suboptimal solution, how much lower is it than the highest? So I claim we have a lower bound on how small this could be as a function of Vmax. So consider the worst case instance that has integers. What's a lower bound on how far apart the best and the second best objective function values are?
1.
1, right? So when we scale by Vmax, then it means that this difference has to be at least 1 over Vmax. Okay? So the smaller the numbers that were being used in this instance, the better the lower bound we have on this gap, okay, between the best and the second best solutions, right? And our intuition should say like bigger gaps are better for us, better for an algorithm, right? The more pronounced the optimal solution relative to everything else, somehow the simpler it should be to find it, right? Okay. So how is this useful? Well, actually, we're pretty much done now. Okay, so here's the algorithm. Right? So we're given an algorithm with polynomial smooth complexity. Here's going to be an algorithm with worst case pseudopolynomial complexity. So 2 steps. So we take this worst case instance after scaling, and now we perturb the values. Okay? And so let me be clear, right? So far, when we were talking about smooth analysis, this perturbation was being done, we were sort of thinking of it at least, as being done by nature, right? It was measurement error or whatever, right? That's not what we're doing right now, okay? We're using perturbations actively as part of our algorithm to solve a problem, okay? These are just fictitious perturbations we made up to guarantee that our subroutine is going to run fast, okay?
To be clear, are we constructing an algorithm that's going to run the pseudopolynomial time or expected pseudopolynomial time?
It's going to be expected pseudopolynomial time.
Okay.
Yeah. So it's going to be a randomized algorithm.
Okay.
Yeah. But it's going to be a so-called Las Vegas algorithm, which is always correct, but it has variable running time. Yeah.
But if it's FP test, can't we just approximate it to 1 over Vmax, and then we know we are...
Well, okay, but then I'd have to prove a connection betwin this and an FP test, which I haven't done, right?
Oh,
so,
yeah, okay.
So on homework, I'll let you investigate the rest of these ideas. Right?
Okay.
Yeah. So we're going to perturb each VI by a random number, delta I, between 0 and 1 over 2n Vmax. Okay? So uniform distribution on that interval. Okay? Independently for each VI. Now, we do pretty much the only thing we can do. Like, remember, this theorem's totally abstract. We know absolutely nothing about this problem. We have no idea what it is. The only kind of foothold we're given is that we're told that we have a subroutine. We're handed a subroutine which runs fast for perturbed instances. So what are we doing? We're making up a perturbed instance. We're going to run A. Think about it, that's all you could do, pretty much. So run A on perturbed instance. And we just return whatever A returns. Okay? So what we need to show is that this algorithm returns, well, basically, first of all, that it solves the problem correctly, and then second of all, that it does so in expected pseudopolynomial time. So correctness, let me draw a picture that's going to be useful a couple times. when we think about perturbations and roundings and other things. So consider the original problem that we had with these worst case values, right? So there is some optimal solution over here, right? So before the perturbation, this was the highest things could get. And then there is some second best solution. And we have this observation that there's a lower bound about how far these are apart, right? So this is at least 1 over V max. Okay, and then we have all this other stuff. Actually, any two distinct solutions have to be 1 over V max apart, but we don't really need that. Okay, we just need it at the top. Now, we perturb things, right? And so that picture changes, right? We're sort of like flicking those little dots around, okay? So imagine that, you know, we're just thinking of holding what the item sets are fixed, but now we're changing the objective function. We're changing the values. Okay, so we're switching from measuring by the values v to measuring by some v hats, where v hats are these perturbed versions of the v's. So all those solutions, the objective function value is going to move a little bit because the objective function moves a little bit. On the other hand, in each component, so we got a couple things going for us, right? So each xi is either 0 or 1. So let's remember what our objective function is, right? So our objective function is just sum over I equal 1 to n of vi xi. Xi is 0 or 1. If xi is 0, who cares? If xi is 1, then it's going to move by whatever vi moves by. Okay? vi is not going to move by more than 1 over 2n times v max by the definition of our perturbations. This thing has n summands. Okay? So in the worst case, it moves by this in each of the n coordinates for a total perturbation of this objective function value of 1/2 or 1 over 2 v max. Okay? So in the worst case, this guy maybe would go downward. Actually, if you look at the way I've defined the perturbations, this can't happen, but just humor me. So we're worried about sort of remember, this is ground truth, right? These are for the real values. And we're worried, in general, about the optimal solution getting worse when we perturb, and other things getting better when we perturb. Okay? And we've pinned everything down. The perturbations are so small that nothing moves by more than 1 over 2 v max. And then they started 1 over v max apart in the first place, so they can't cross. Okay? So the relative ordering of everything, actually, in this case, but in particular of the top two solutions, remains the same. There's no inversions. Okay? So this movement and this movement, at most 1 over 2 v max. And of course, there's no magic there. That's just how we define the perturbations. We defined it so it would be true. Okay? So correctness, each solution perturbed by less than 1 over 2 v max. So with probability 1 over the perturbations, the new optimal solution was an old optimal solution. Okay? If we started with many solutions that had exactly the same objective function value, they won't in general all still have the same objective function value. But the point is, you know, whichever the best of those after the perturbations, that'll be our new optimal solution. Okay? And that was one of the optimal solutions to the original problem. So that's correctness. Right? Basically, we solve a perturbed problem, but the perturbations are so small, the optimal solution is exactly the same, so we can just, it's legit to just return the optimal solution of the perturbed instance. Okay, running time. Also straightforward. So, by assumption, the subroutine we were handed A has a polynomial smooth complexity. So that means its expected running time is poly in n and 1 over sigma, where 1 over sigma is an upper bound on the density. Because we're picking things uniformly from an interval of length 1 over 2n v max, that means 1 over sigma is exactly 2n v max. Right? This is that case where you're just uniform on your support. Okay, so the density is just the reciprocal of your area. So, our expected runtime is just this, plugging in nv max, 2nv max for 1 over sigma. Okay? And that's pseudopolynomial. Okay. Any questions about that? Yeah.
Wait, so are you saying that all the VIs are integral?
Yeah, I mean, if they're not, I mean, the VIs are given as just binary numbers.
Okay.
They're just represented, right? And so I'm just saying, if you want, interpret them as integers. So if you want, first scale them up, or just, first clear denominators to make them integers, and then scale them back down to put them in 0, 1. Yeah. Yeah. Other questions? Okay. So you might wonder, is this direction good for anything? So after all, we could apply it to something like knapsack. And what does it do? It gives us like a randomized pseudopolynomial time algorithm for knapsack based on what we proved last lecture. Right? So last lecture we proved knapsack has smooth polynomial complexity. So we can feed it into this reduction and get a randomized pseudopolynomial time algorithm. It's not really something we needed, right? We learned in undergrad algorithms one or more deterministic pseudopolynomial time algorithms for knapsack that probably had better running time than this. And also, we didn't have to work so hard. We didn't have to do all that stuff last lecture. So, you could imagine maybe other problems where this will get you a novel randomized pseudopolynomial time algorithm. I'm not saying those don't exist, but I don't think that's the number one reason to care about this. I think the number one reason to care about this is actually the contrapositive, so negative results, okay? And understanding problems which cannot have polynomial smooth complexity. So, notice, by the contrapositive, if a problem cannot have a randomized pseudopolynomial time algorithm, then by this reduction, it also cannot have polynomial smooth complexity. Okay? So this is sort of like the perverse direction of using this reduction, the dishonorable direction, where you expand the frontier of negative results. So what? So are there problems that we know cannot have pseudopolynomial time algorithms? Well, yeah, actually. We know that almost all NP-complete problems cannot have pseudopolynomial time algorithms under suitable complexity assumptions. There's a notion of a problem being strongly NP-hard, and the whole point of the definition of strongly NP-hard is to say that you cannot have a pseudopolynomial time reduction. So I'll ask you to look up that term and talk about this a little bit on homework 8, okay? So what it says is, while there are problems like knapsack and some other so-called weakly NP-hard problems where the complexity drops from hard to easy when you switch to smooth analysis, for most NP-complete problems that will not be the case. Okay? And we learn that from this reduction. That's, I think, the main reason to care about this direction.
Is there a way to use this to get a deterministic algorithm?
I don't, totally generically it seems hard to me. Unless you knew that A, right, because you know nothing about A, right? So how would you de-randomize a totally generic A? So if I told you that it had smooth complexity in some sense that, like, for a worst case perturbation, it was still polynomial time, but then that would actually imply that that problem was polynomial time solvable anyways. So you'd have to have some assumption, I think, on the prospects for de-randomizing the subroutine A in some limited sense. So it seems tricky. I guess the way I think about it that way is if you can use this reduction for some problem you actually care about to get a randomized algorithm, then I would zoom in and just focus hard on that problem and say, like, this is good evidence that some deterministic thing must exist. What does it look like? But then maybe start from scratch using the specifics of the problem. I think that's kind of the takeaway more. Okay. So that's nice. We sort of know that killer applications for problems going from hard to easy, we should be looking at weakly NP-hard problems. Those are the pseudopolynomial time algorithm. So now sort of the best case scenario is that any problem with a pseudopolynomial time algorithm actually does have polynomial smooth complexity. And very happily that actually turns out to be the case. So let's prove it. So so just again, sort of a quick preamble. So we're going to be given, so now the assumption is that the algorithm admits a pseudopolynomial time algorithm A. Okay? We need to show that its smooth complexity is low, it's polynomial. And so this is where we're really doing something different, right? We're really not fixing an algorithm and analyzing it. We're really saying, given that our goal is polynomial smooth complexity, what kind of clever algorithmic ideas can we devise to come up with something new that actually meets that goal? Okay? So here we're really starting with the analysis goal up front, and then we're designing the algorithm crafted to that goal, as opposed to the last couple of lectures, which were the reverse.
It's very a rather vague question, but I thought that if we could solve a single NP-hard problem in polynomial time, I thought theory then implies that we could solve every problem, NP-hard problem in polynomial time.
That is correct for worst case polynomial time computation,
For worst case polynomial.
which is not what I've done for you.
No, okay, but so there's not a polynomial reduction of other. So for example, if we had another NP-hard problem and we could do polynomial reduction to knapsack, then we could use this, right?
And then the question would be, how do you interpret what you get, right?
Well,
So what's the distribution?
So then this problem also has to be.
So where's your distribution come from? So let's start with SAT. Are you proposing a notion of a perturbed SAT instance? Or not? Or are you going to run the reduction and then perturb it?
I don't know. So I'm going to run
I think you'll find it challenging to come up with a sensible notion of a perturbed SAT instance.
Okay.
And if you reduce SAT to knapsack and then perturb, you have the problem of trying to map back your knapsack solution. Or in particular, I'd say it's for decision problems. You have to prove that after you perturb it, you've retained, you still are respecting the yes/no of the original hard SAT instance. And the hard SAT instances are going to be ones that give you knapsack instances right on the edge of being satisfiable or not at a given target. And so it's where you expect perturbations to turn it into a 50-50, who knows, kind of situation. Okay? Yeah. Good question. Other questions? All right, so the converse. So now we know what we want. We want polynomial smooth complexity, and all we've got to work with is some black box, which runs in worst case pseudopolynomial time. How do we use it? Well, let me first tell you about the key analysis tool we're going to use. Okay, so I'm not going to tell you the algorithm yet. I'm going to tell you this really nice lemma. And so I'm going to call this the isolation lemma. Not to be confused with the original isolation lemma, which I'll put on the homework just sort of for educational reasons. That was developed maybe in the 80s for parallel matching algorithms. But it turns out the same idea is hugely useful here and for some of these smooth analysis problems, which is just sort of a very cool connection. And what we're going to do here will be familiar to you now that we've done a couple of these smooth analyses. So this is going to be the part where we identify a bad event, which is simple enough and sort of just aligned enough with everything else that it's really easy to upper bound the probability that this bad event happens using the fact that it's a smooth instance. So in the last lecture, we worked really hard, and then at the very end of the lecture, we finally had such a bad event. Here I'm just starting with this bad event, and we're just going to analyze it. Okay? And then I'll show you how, building on this, we can get what we want. We can get smooth polynomial complexity. So for this binary optimization problem under discussion, and actually this lemma doesn't need there to be a pseudopolynomial time algorithm. Okay, so this will actually be true for any binary optimization problem, easy, hard, or whatever. So fix an instance, and for a parameter epsilon, we're going to call an index or a variable epsilon bad if we do two thought experiments. First, we say, okay, so the real optimization problem is to optimize this value over all feasible sets. Let's say, well, first of all, what if I made you include item I, if you will, in the knapsack terminology? What if I forced you to set xi equal to 1? And then I forced you to, and then you could maximize over the rest. And then I do the same thought experiment with xi equals 0. Okay, so I'm going to get two solutions, one with xi equal 1, one with xi equals 0, each best with respect to that constraint. Of course, the better of those two will just be the optimal solution of the whole instance. because the optimal solution either has xi equal 1 or xi equal 0. But one of them will generally be inferior. And the bad case is where those two solutions have almost the same objective function value. Okay, so you're almost agnostic as to whether I force you to set xi equal to 1 or I force you to set xi equal to 0. It barely changes your optimization problem. Okay, that's going to be our bad event. So if the opt solution with xi equal 1, let's say optimal solutions with xi equal 1, xi equal 0, have value within epsilon of each other. Okay? So that's going to be our bad event. It's actually quite easy to prove an upper bound on the probability of this bad event. So specifically, let's show that the probability, so we're thinking about a smoothed instance now, okay? So I should say that. So the probability here is over the perturbations of the VIs. Okay. So probability that there exists an epsilon bad index I is at most epsilon n over sigma. Okay. So the smaller the epsilon, right? So the worse the event, and the smaller the upper bound on the probability. The more spiky, the bigger 1 over sigma can be, the more spiky the distributions, the worse our upper bound, as you'd expect. Okay, so this is the bad event, and we have more and more control over it as the distributions are less and less spiky. All right, and so this proof, it resembles to a large degree our proof in the Pareto curve lecture when we finally were upper bounding the probability of those indicator random variables NIT, if you remember that. Okay, but this is definitely a little bit simpler, but it's very similar. So we're trying to upper bound that any index I is bad. Fix your favorite. So let's upper bound the probability that a fixed index I is bad. And again, in the spirit of the last couple lectures, we're going to show that I alone, so VI alone, has enough randomness to give us a good upper bound on this event. So we're just going to get rid of the rest of the randomness, and so we're proving an even stronger inequality. So condition on Vj for all j not equal to I. Okay. So let S minus I and respectively S plus I denote the optimal solutions with xi set equal to 0 and to 1. And so now let's notice, because there's so little randomness left, at this stage we know a ton about S minus I and S plus I. So S minus I, actually, we know everything about it. What is S minus I? It's the best solution where xi equals 0. Okay? We know the value of everything other than I. And so we don't know VI. But if xi equals 0, who cares about VI? Doesn't matter. Okay? So what we're optimizing over, it's independent of VI, so they all just have these fixed values. So there's just one of them which is the best. Okay? So S minus I is just fixed. And again, remember throughout we've conditioned in this part of the proof on Vj, all j not equal to I. And we even know the exact value of S minus I, because we fixed the values of all the x's for which it sets to 1. So also its value V minus I. Now, and again, this is very similar to last lecture. The identity of S plus I, okay, I also claim is now totally fixed. Okay? We know which feasible, among all feasible solutions, for which xi equals 1, we know which of those has the maximum value. And there may be this sort of initial pushback, like what do you mean? We don't know what VI is yet. But of course VI, whatever it is, contributes exactly the same amount to every feasible solution with xi equal to 1. So the relative ordering of the values of all the solutions with xi equal to 1 is independent of VI. Okay? So we actually know what S plus I is. So identity of S plus I is fixed. And we don't know its value, because VI is still random, but we know its value has the form x plus VI, or x is fixed. Okay? And it's actually, there's no mystery what capital X is. You just look at this best solution, S plus I, you look at the coordinates where it's set to 1, other than I, and you add up all of those values. That's what capital X is. Right? And then it's going to get this bonus from VI, and we don't know what it is. Okay? Everyone agree with that? This is the subtle point. I mean, the good news is you saw something even a little trickier than this on Wednesday. So it's sort of like a slightly simpler version of that. Okay. Good. So how could it be that this index I winds up epsilon bad? Remember, epsilon bad means the best solution with u set to 0 and the best solution with u set to 1, they have almost exactly the same total value. Okay? So why is that unlikely? So what would have to happen? Okay. What would have to happen? Well, basically, we have this solution with xi equals 0, the best one with xi equal to 0, and it has some total value, 1,237. Okay? And the only bad case is if this winds up within epsilon of 1237. Right? That's the only way that index I will be bad, conditioned on all the other VJs. So that means the only way it can happen is if VI lies in this little interval of length 2 epsilon. Okay? Basically, it has to be equal to V minus I minus X plus minus epsilon. Okay. So I is epsilon bad if and only if VI winds up being essentially equal to the value of the optimal solution with xi equal to 0 minus all of the stuff the best solution with xi equal to 1 gets other than from VI plus epsilon error. Okay. So again, this is just one smooth random variable landing in an interval of length 2 epsilon. The density is at most 1 over delta everywhere, so this is probability at most 2 epsilon over delta. Okay. So since fi of x is at most 1 over delta, 1 over sigma for all x, probability I is epsilon bad is at most 2 epsilon over sigma. Agreed? Just by the density upper bound. So we're just done by the union bound. Right? So a given fixed index I, there should be a 2 there, is bad with that probability, and there's n of them to take the union bound over. Okay. So done by union bound. Okay. Yeah. Any questions about that? Okay. So that's the claim. Let me now show you how this easily implies what, for this lecture, I'm going to call the isolation lemma. So corollary, and here's what I mean by the isolation lemma. Probability, and again, this is over the perturbation, that the optimal solution value minus the second best value. So here it is again, that gap between the best and the second best. I told you it would be a theme. Okay, so here it is again. So after you smooth the instance, the probability that this gap is small, meaning at most epsilon, where epsilon is your favorite parameter, this is bounded by exactly that same probability. Okay? So let me tell you why. So the proof of this, given what we've already done, is just, well, the proof of the claim's like 2 lines. The proof of this is going to be like 1 line. But the statement actually is kind of amazing, really. It's kind of cool. Like, it sort of corrects a bad intuition that most of us wind up having. Let me explain. Like, this seems to almost contradict the pigeonhole principle in some sense when you first see it. So let me explain. So imagine epsilon. You know, think of epsilon as pretty small, but like inverse poly. Epsilon's maybe like 1 over n squared or something. Okay? Sigma, you know, some constant. Sigma is 10 or whatever. All right? So with those parameters, then this is going to be a nice small number. Okay? This is going to be like theta of 1 over n. Okay? If epsilon's like 1 over n squared. Okay? And so right, epsilon's the gap between this first best and second best solutions. So let me tell you why that's surprising. Okay? How many different feasible solutions are there potentially? There's like 2 to the n potentially. I mean, it depends on capital F, but I mean, it could certainly be exponential in n. What is the spread of total values? Okay? What is the interval of total values in which these exponential in n solutions lie? How small could they be, the total value? 0. How big could it be? When we remember where the VIs, remember, between 0 and 1. Okay. So it's the most n. Okay? So we have like 2 to the n solutions thrown into this thing of interval n. So if the values of these were equally spaced, there would be an exponentially small gap in between consecutive items, consecutive solutions. And indeed, on average, that has to be true, right? I mean, there's just, you pick a random pair of consecutive solutions, meaning like, you know, the kth best and k plus first best for an average value of k, they really will be exponentially close to each other. Yet somehow here, because we're talking about the best and the second best, actually they're only inverse poly away. Okay? So in other words, I can take epsilon equal to 1 over n squared here and it's fine. Okay, there's only an n in the numerator. There isn't a 2 to the n in the numerator. Okay? So that's what's amazing. Because we're looking at the very top of the values, they're far more spread out than they are in the middle of the distribution or even on average. Okay? Yeah, in some ways this is the bell curve, exactly. In some ways because we're at the very tail of the bell curve and things are sparse. And this is making that precise.
Can you construct an input where this isn't the case?
Where what's the case?
Where you don't have that large spread right at the top. Can you construct an input where they're evenly distributed?
Well then this would be false, right?
Yeah.
So no. Yeah. So that's why, and that's where the name of the isolation lemma comes from. Somehow the best solution is isolated, you know, it's lonely at the top, basically. All right. But we've really already proved it. So how do we just go from this claim to the isolation lemma? So let S1 be the best. Let S2 be the second best. In particular, they're not the same. So there exists some variable I set to 0 in one of them and 1 in the other. So suppose Oh yeah, I should say, there's a word for this in this context. In smooth analysis, this is sometimes called the winner gap. Okay, so the gap by which the winner is indeed the winner. So suppose the winner gap was actually small, okay, less than epsilon. How could that possibly happen? Well, then it must be the case. Okay, so So suppose S1 has xi equals 0, right? It's certainly the optimal solution for which xi equals 0. Similarly, S2, if it has xi equal 1, it's the optimal solution amongst everything with xi equal 1. Okay? So if this is less than epsilon, if the winner gap is less than epsilon, then by looking at S1 and S2 and choosing I as an arbitrary element, which is 0 and 1 and 1 in the other, we exhibit an epsilon bad index. Okay? So every time the winner gap is less than epsilon, we can witness it with an epsilon bad index. That means this is a necessary condition for this, so this probability can only be smaller. Okay. So if winner gap less than epsilon, then this I is epsilon bad. So any questions about that? And again, this stuff, everything on the board right now holds for any binary optimization problem. Okay, easy or hard. It turns out it's just useful when the problem isn't too hard. Okay. All right. So let's get to the algorithm design. So now we're going to assume, in addition to being a binary optimization problem, that it has a pseudopolynomial time algorithm A. I'm cheating a little bit. For simplicity, I'm going to assume that A is deterministic. I'll let you check that exactly the same argument would work if A was randomized pseudopolynomial time. Okay, it really doesn't matter. But think of it as deterministic. All right, and so this is worst case pseudopolynomial time algorithm. We need to prove a smooth complexity bound. So the good news is we get as input a smoothed instance. Okay? So we're given a smooth instance. And again, remember the VIs are in 0, 1, drawn from a not too spiky distribution, density at most 1 over sigma. So here's our algorithm. And the algorithm, it's a quite nice algorithm. It's not clear to me, it's conceivable one could have come up with this algorithm without having a smooth analysis motivation, but I'm not sure, at the same time, I'm not sure it would have ever happened. So here's our new algorithm. So we have a loop. And so what we do is we successively unveil the bits of the values. Okay, so we're given VIs as values, and we unveil their bits one by one, obviously from the highest order bits to the lowest order bits. Okay. So let V hat I denote the first B bits of VI. Let me just make sure it's clear what I mean when I also say all the VIs are between 0 and 1. So let's just make sure what this means. So when B equals 1, you're just seeing the highest order bit of everything. So you're just seeing a 1 if VI is at least a half. And you're seeing a 0 if it's less than a half. Okay? Once you see the second bit, 1, 1, that means it's at least 3/4. 1, 0 means it's between a half and 3/4, and so forth. Okay? So that's what we're doing. Right? Between 0 and 1, and we're just sort of learning, the relevant power of 2 each time. So notice v hat depends on b. You're going to keep recomputing v hat, but I'm going to suppress the notation on b. Okay, but remember v hat, that's really with respect to a fixed iteration, a fixed number of bits. Okay? So the good news is when b is small, these are small numbers. Okay? They have small encodings, so a pseudopolynomial time algorithm is going to run fast. And we have in our hands a pseudopolynomial time algorithm A. Okay? So we use A to compute the feasible solution x hat, which by definition is the one optimal for v hat. Okay? Now, our task is not to be optimal for v hat. Our task is to be optimal for the true input, the actual VIs, the actual values. And so especially early on, when we're looking at only a few bits, you might think we've taken such a coarse approximation of the input that when we solve exactly for this coarse approximation, we get something which actually isn't totally optimal for the real input. So intuitively, we want to keep unveiling bits b until we're sure we've got the right one and we don't need to look at any more bits. Okay? So let me state this informally, and then I'll explain exactly how we implement it. But the point of step 3 is the stopping criterion. So what we want conceptually is that if x hat, okay, so we compute x hat by definition optimal for the truncated things, the v hats. If x hat happens to be optimal for v, and now you should complain. You should say, well, we don't know v. We haven't looked at v. We've looked at the first b bits only. Fine, okay. But suppose x hat was optimal no matter what the unseen bits are. That would be good enough for us also. Right? Then we don't need to look at anything more. Right? We can just conclude we're optimal. Okay? So that's going to be the idea. So we're never going to look at all of v, but we're going to nevertheless have a certificate that whatever v is, we're optimal for it. Okay? So no matter what remaining bits are, at that point we stop and we return x hat. Okay? So, comment. So as far as the running time, so step 2. So because A is pseudopolynomial, remember one way to think pseudopolynomial is that you run in time exponential in the representation of the numbers you're working with. Okay, so it's b bits, so it's going to be something like 2 to the b. Okay, so this runtime is going to be polynomial in n and 2 to the b in iteration b. Okay, because it's a pseudopolynomial time algorithm. All right. Okay. So, the question then is, what does this mean? Right, so it's sort of clear, if we could actually faithfully implement step 3, I hope correctness is clear. Right? So we have something x hat in our hand. If a little birdie told us, I'm not going to tell you the rest of the bits, but whatever they are, this is optimal, of course you can stop. Right? You don't need to look at them. So let me actually show you we can implement this step in a nice way, just running A again, actually. Okay? And the intuition is very simple. We just want to say, look, we're crossing our fingers, right? So we took this coarse approximation v hat of the true input, we got some feasible solution x hat. We're crossing our fingers that actually, even though we solved this coarse approximation, we got the right answer for the real problem. We really want x hat to be optimal forevermore. So what we want to have happen is we want to well, if in our head we ran this algorithm for b going off to infinity, x never changed. X just stabilizes. Okay, we keep running A, we keep getting x hat back over and over again, even as we feed more and more data. So how would that not happen? What are we worried about? What's the concern? The concern is that as we learn more about the true values, the v's, this x hat starts looking a little less desirable than it used to. Okay?
And the second best one gets a little bit more valuable.
Right, so let's think about this. Let's drill down. So what would it mean? So when we see the next round of bits, okay, we have x hat in our hand, and it's our protagonist. We're rooting for it to stay optimal, right? But then we see some more bits, right? What could go wrong? 2 things could go wrong, okay? So first of all, on a variable in x hat, which we've set to 1, the worst case for us is that the next bit's a 0, right? So imagine like the first 2 bits were 1 and 1. So we know it's between 3/4 and 1, right? and we're sort of hoping it's high, right, because we're including it, right? But maybe we see a 0 and now we know it's at most 7/8. Maybe we see another 0 and we know it's at most, you know, whatever, 13/16, et cetera, okay? So 0 sort of makes things look less attractive than we thought. Similarly, whenever we have an xi equal 1, okay, if we have an xi equal to 0, something we're not taking, then we're concerned the next bit's going to be a 1. All right? So if the first two things were 0, 0, we know it couldn't be better than a quarter. But then, you know, as soon as we see a 1 in the next iteration, we know it's at least an eighth. If we see another 1, then we know it's at least, you know, whatever it is, 5/16, 7/16 or something. Okay? So the intuition is, you know, we have x hat. If all we ever saw were 1s, where we already have xi equal to 1, and 0s, where we see xi equal to 0, we'd totally be done. Okay? But if it flips, if it's completely the opposite, we've got to be ready for x hat to switch to something else. On the other hand, if we could somehow just recompute the optimal solution for these worst case settings of the rest of the bits, and we still got x hat back, then we're golden. Okay, so that's the insight. We actually know, right? We obviously can't check everything the rest of the bits are, but we can characterize what is the worst case setting of the remaining bits. We can recompute just for that and see if we get the same solution x hat back. Okay? So that's the idea. So let me just be precise about it. So for each I, what I'm going to write down is I'm going to write down, you know, an approximation of sort of the worst case scenario for x hat for, you know, the rest of time immemorial. So as we discussed, if it's something that we're actually setting equal to 1, then the worst case for us for the persistence of x hat is to only see zeros. Okay? So in this case, I'm defining v bar, a new v bar. And so v bar is just going to be equal to our truncated version, which corresponds to seeing zeros for the rest of time. Right? So vi hat, that's only taking the first b bits. If I pad it with zeros for the rest of time, that's v bar, and it's the same number. Okay? That's the worst case for the things we're already taking. So for something where it's currently set to 0, we've seen the first b bits, it's currently 0. The worst thing is everything else is 1 from now on. Okay? And we don't want to actually keep track of all those 1s. We'll just add 2 to the minus b, excuse me, to v hat. Okay? So in this case, we set v bar I to be v hat I plus 2 to the minus b. Okay? And the point is, in that second case, that's an upper bound on what the real input is, no matter what the bits are. Okay? Even if all the remaining bits are 1, that's still an upper bound on the real value vi. Okay? And so now to implement 3, what do? We're going to recompute x bar optimal for v bar. And the point is, this is just one more computation of the type that we've already done. Okay? It's exactly the same number of bits, and we're still using just b-bit numbers, and we're invoking the same algorithm. Okay, so poly and n and 2 to the b. Okay, so analysis. And again, the picture you want to have in mind is that same kind of, we have the axis of the objective function values. And we're plotting things, and things are here with respect to the real values, the v's. And now we have two different rounded versions of the true values, the v bars and the v hats. Okay? So if the green dots are with respect to the correct values, which we haven't looked at yet, then if we switch to optimizing instead with respect to the v hats or the v bars, each of these will have a little shadow nearby. Okay. If we switch the objective function a little bit, then each of these will change a little bit. And so now the plan is the same thing that we've already seen. We're going to show that the v hats and the v bars are close enough to the real ones that things can't move too much, and that keeps us out of trouble. Okay? So that means, ultimately we really have to do the proof in a quantitative way, because we really care about how big b needs to get before we trigger the stopping condition. Okay? So don't forget, we're invoking a pseudopolynomial time algorithm, so our running time is exponential in the representation of the numbers that we're using. The running time is 2 to the b. Okay? So if we prove that we need to take b up to n to trigger the stopping condition, we're toast. Okay? Even like log squared, we would not be very happy actually. Okay? So we really want to say that by the time b gets to logarithmic in all the parameters we care about, the stopping condition will be triggered. Okay? That's what we need to prove. So let's do it. Oof. Let's do it quickly. Good. And did I finish this? Yeah. So if x bar, yeah, okay, good. So notes, so let's proceed to understanding how different things are with respect to these different objective functions. Okay, so first of all, if the x hat we compute in step 2 winds up again being optimal for v bar, then we're done. Okay? And that's just by definition. We define v bar to be the worst possible ones. The real inputs are not as bad for v hat as the v bars. So if even the v bars give us back an optimal x hat, then we can just return it and we're done. So if x hat opts for both v hat and v bar, also for the true input v. Okay? Which is really cool because we never looked at even most of v. Right? So it's pretty neat. So now let's get a handle on how closely our two rounded objectives approximate the true one. Okay? So let's start with the truncated version. Okay, so remember we're fixing an iteration b. So this is by definition the first b bits of vi. Okay? So is it bigger or smaller than vi? Smaller, right? You've just thrown off some of the trailing bits. Okay? So this is in some interval where the right-hand side is vi. Okay, it's a most vi. How much smaller could it be than vi? Roughly. Right. Okay. So because you've seen its most significant b bits in the residual, there's only 2 to the minus b possible range there. Okay. So the most you could be off is 2 to the minus b. All right. So how about for v bar? Is v bar bigger or smaller than v? V bars are defined over there.
It's either the same or bigger.
So you're saying it can't be less.
Yes.
So remember, sometimes v bar equals v hat. And we just argued that v hat can sometimes be less. But it's a good point that it can be bigger.
So that could be less or bigger.
It could be less or bigger. By how much in either way?
2 to the minus b.
Right. Okay, so the v bars, it depends on what's up with x hat. Okay, we have 2 definitions. In one case, we're underestimating, and the other one, we're trying to correct for the underestimation, but maybe we weren't underestimating, so then we'll end up overestimating. Okay. So that's what we know about the extent to which v hat and v bar approximate v component by component. Okay. So let's think about going from just individual coordinates to entire feasible solutions. So our objective function is just the sum of, at most, n of these vi's, right? So if you're just talking about to what extent does the objective function value change, it's just going to be these same numbers with the error terms multiplied by n. You might get that accumulating from each of the coordinates, okay? And let me just be a little sloppy and sort of consolidate everything and say for all x, what we have is that the objective function with respect to either v hat or v bar, this is going to be within n times 2 to the minus b of the true objective function v transpose x. Okay? So this is just immediate from b. Okay? All right, and so relating that back to this picture, that says if the green dots represent the true objective function value v transpose x, then whichever one of v hat or v bar we switch to measuring instead, we get these perturbations in potentially either direction of magnitude up to n times 2 to the minus b. Okay? So one thing that's maybe nice to see is that once minus b starts hitting log n, then we start getting some control over this error, okay? Which we're pretty pleased to see, because we know we can only tolerate b up to about log n in our running time, okay? All right, so upshot. Is that we're done. So here's the claim, and this sort of summarizes all the work we just did. We're done once the winner gap is at least 2n 2 to the minus b. Okay? Now I phrased this in a way that might be confusing, so let me clarify. Right, so we're just given this smooth instance, okay? And they're just these values. And it has some fixed winner gap, okay, once you sort of fix the values, okay? The optimal solutions, 1,037. The second best one is 1,023. The winner gap's 14. Okay, so it is whatever it is. So what I mean here is that, but think about as the iterations of our algorithm proceed, b keeps getting incremented, okay? So the winner gap's whatever, like 14, but as we keep incrementing b, this keeps getting smaller, okay? So there'll be some value of b, the first one, at which that right-hand side is less than this winner gap, okay? So the question is, how big does that need to be? Okay, and then why are we done once this is true? Well, once the winner gap is bigger than this, that means even if when we look at v hat and when we look at v bar, even though the objective function values of feasible solutions might be changing by most of this much, there's still such a big gap between the first best and the second best solutions. Even if the first best gets decreased by the maximum amount and the second best gets increased by the maximum amount, it will still be the case that whichever of these objectives we're using will correctly rank those top two solutions, okay? So it doesn't matter if we optimize with v hat, or with v bar, we always get back the same solution, the optimal one for all three of them simultaneously, okay? And at that point, the algorithm certainly terminates. Okay, so now the question is, when is this going to happen? Okay, in a smooth instance. So recall this. Okay, so the point of the isolation lemma was to give us control over how likely the winner gap was to be of being small. So the winner gap is only at most epsilon, that's probably 2 epsilon n over sigma. Okay. So probability, let's see. So let's say, how do I want to set the parameters here? So basically, all right, so to get probability of winner gap, let me just set the parameters. Okay. So take delta equal to 2n over sigma, n times 2 to the minus b. And then by the isolation lemma, probability that the winner gap is at least this amount, 2n 2 to the minus b, will be less than delta. Okay, so that's just solving. That's literally just setting this to delta and setting epsilon to what we want it to be, that winner gap, and then solving for b. Okay? So, equivalently, this becomes at most delta, so the probability of this bad event becomes at most delta as soon as b becomes log of n over sigma times delta. So again, 1 over sigma, that's our upper bound on densities. Delta, this is a free parameter. Okay? So you pick delta however you want. If you want an upper bound of delta on this bad probability, then once b hits log in n over sigma delta, that's when the probability gets that small. Okay? All right, so let me summarize all this. So thus, for all delta, the probability that the algorithm halts, so now remember, the running time is polynomial in n but exponential in b. So we're going to pick up so that the exponential will cancel that log. It'll be polynomial in n, 1 over sigma and 1 over delta. Okay. So the probability that the algorithm halts in time poly n 1 over sigma 1 over delta is at most delta. Okay? For whatever delta you want. Okay, so this is true simultaneously for all deltas. Okay? So that's good. So if you think about it, I mean, you could even set, I mean, for starters, you could set delta to be like 1 over n squared. Okay? So this would say that this algorithm, this one which just unveils the bits one at a time, keeps using A to compute something, and then checking with these worst case V bars to see if you get the same thing, and stopping as soon as you get the same thing. That algorithm, within smooth polynomial time, poly and n and 1 over sigma, it completes with probability 1 over, sorry, it does not complete, I see the problem. Sorry, this should be the complement, yeah. My bad. So it does not halt with probability at most 1 over delta. Sorry, with probability at most delta. It does halt with probability at least 1 minus delta, okay? So with an only 1 over n squared failure probability, it terminates in polynomial time, okay? So that's not quite the definition of smooth complexity we've been using. We've been using that the expected running time should be polynomial, and that's a slightly stronger statement. However, with a minor tweak to the algorithm, once you have this guarantee, it's very easy to actually extend it to an algorithm that does have expected polynomial running time. Okay? So that's the upshot. So basically the failure probability is decreasing sufficiently quickly in the number of iterations B, so that even though you have exponential running time in B, you start getting negligible probability of having to go forward once B hits logarithmic and all the relevant parameters. Okay? Any questions? Yeah.
By the isolation on that, I'm confused about why it's the probability that the winner gap is greater than 2 under 2 minus delta is bounded by delta.
Should that be less than?
I don't know.
Yeah, it should be, you're right. That's the bad event, right?
Right, because we want the winner gap to be a certain size, right?
That's right.
To be at least.
And then it also matches up with that inequality too, yeah. You're absolutely right, so I had this flipped. Right, so the bad event is that the winner gap is small. Because the winner gap is big, then you terminate, right? That was the whole point here. If the winner gap for a given B is big, you're definitely done. So the bad case, the bad event when this is too small, so we're invoking the isolation lemma with epsilon equal to our desired gap, 2n 2 to the minus b. And then that's at most delta when b hits this amount. Okay? So the way to think of it is, so here is just some epsilon. Our previous analysis tells us the epsilon we care about. Okay, the epsilon we care about is exactly this number. Okay? Because being below that is the only way we're not going to stop. Then we just threw in a free parameter delta. Okay? And then we just said, okay, let's solve for the b when, indeed, the right-hand side here, our probability upper bound becomes less than delta. And this is the b that we get. And then we're very happy to see all of the parameters popping up in the log there because the running time is exponential in b. Okay. Sorry for going over. I'll see you Wednesday.